Okay, it's a pleasure to be here, especially to do this on behalf of Planck collaboration on this first rather important day in its existence. I will speak about early astrophysics results that are being released today to the community. I brought a couple of posters. This one you may have seen. It's been released by ESA in July and shows the composite image from 9 frequency bands of Planck, rendered artistically by graphics experts of ESA into a full sky image, combining all contributions. We'll see it on the screen later. The opposite side of it describes some aspects of Planck. This is the poster that we prepared in the US team for the AAS meeting, which is ongoing now in Seattle. Like I said, I have a few, not too many. If you want to ask me for one, I'll give you them. I won't bring them back with me. So after the talk, don't be shy. This is Planck, the machine that we're operating now since May 2009 in space. It's a so-called third generation mission to measure microwave background anisotropies and various aspects thereof. Third, as in following up on the first generation with COBE and the second with WMAP. Very different instrument. It's time with the release of new data to maybe briefly recount what the principal differences are between Planck and prior missions, especially WMAP. So what you see here is a single telescope looking at the cold sky on top of the satellite pass, screened away from hot space, away from Earth and Sun and Moon behind that screening shield, with a system of passing cooling radiators called V-groove, on top of which the cold part of the experiment sits. The principal difference between Planck and WMAP is that Planck is actually a combination of 2 instruments. One is radiometric, like COBE, DMR, and like WMAP, and observes the sky at low frequencies. And the other one is bolometric, and at 6 frequencies observes the sky in an actively cooled system. WMAP was a satellite which employed only passive cooling to dump heat from the platform and observe the sky with detectors in the focal plane operating I think around 40 Kelvin temperature. The difference is that if you look, this is a reflection on the screen of the focal plane, which is really here, but it's better seen on reflection, with big horns of low frequency instruments surrounding an orange box of the most cooled part of Planck. That is the detector box for high frequency instrument housing all the bolometers. And this operates at 100 millikelvin temperature and is very likely the coldest object in the solar system. We need to cool it to gain sensitivity, and the sensitivity gains are tremendous over the previous mission, and I will describe other gains elsewhere. I represent the US part of the team working at JPL, so let me briefly state here that thing that usually is not overstressed, since Planck is a European Space Agency mission with significant participation from NASA, it sort of falls off the cliff for people to understand that design of this extremely efficient passive heating, passive cooling stage on Planck was designed, was committed at JPL, and it performs splendidly. What you don't see housed inside the satellite are the first stage coolers that bring the temperature down to around 20 kelvins, the so-called sorption coolers that operate without the moving parts and start a chain of 3 stages of active cooling that go through Joule-Thomson cooling, taking down temperature of the system to 4 kelvins, and then going through dilution, helium-3, helium-4 cooler, which provides the 100 millikelvin temperature for bolometers. So the first stage of active cooling from JPL, and also all the bolometers inside the HFI instrument have been built at JPL. So fairly essential technological contributions to the mission. The total tally for NASA is in excess of $100 million. Includes the cost of building the catalog that is being released today, and data analysis that went into it, and support of the data analysis team, which mostly operates right now as the final part of US participation. Hardware is delivered, of course, long ago. Planck has been proposed and designed to measure CMB anisotropies to the fundamental limits of about angular scales down to 5 arc-minutes on the sky, with the added-on goal of measuring polarization of the CMB. As Alessandro already alluded, and you surely know, in order to get to these two targets, you have to dig through some serious foregrounds, as in the poster. Everything white, not so good for CMB science. It has to be managed in the best way possible in order to get to, especially, eventually, very low amplitude polarization signals. In order to separate these foregrounds efficiently from cosmological signals, you better make your measurements over a wide frequency range to provide measurements from your instrument, preferably at the sensitivity range that you control, as there is very simply not very much ancillary data that will help you doing this job, because other people measured it better. If they did, you wouldn't have to do the job. Right? So we have to do the foregrounds very well, and the scope of this meeting is precisely that. Everything I will talk about today is foreground astrophysics, and in fact mostly focused on compact source aspect of it, rather than diffuse, because, as I said, the principal product released today is the released compact source catalog. This is an old plot which shows on the map of electromagnetic frequency from 10 to 1000 gigahertz where we're operating. So the center of this plot is the classic 100 gigahertz division line, which typically splits operation regime of radiometric instruments at lower frequencies from different volumetric, typically instruments operating at higher frequencies. So it is for Planck. The 3 low frequencies are LFI instrument, WMAP for attention operated from slightly lower frequency at 20 gigahertz down up to 94 with overlap and excess frequency, which Planck unfortunately doesn't have. Now, the gray bandwidth indicates the bandwidth of the particular detectors that are looking at the sky at each center frequency. We plot here the brightness temperature at the equivalent scale of about 1 degree on the sky for CMB contributions, which we are trying to dig out, fighting against foregrounds, which very schematically are represented here by the 3 classic components that we're fighting against: the dust in our galaxy, which has a rising spectrum, the synchrotron emission, and free emission, which have a falling spectra, which define the classic minimum. The sweet spot for CMB measurements roughly around 70 gigahertz. For temperature, quite well established. Not so clear yet what the situation is for polarization. Early indications from WMAP are it's not very different. So that's where you hit and target CMB anisotropies.
What are the round stripes?
What are what? This?
Right.
They indicate the width of the band at which detectors operate. Gain their sensitivity looking at the sky. This is the image of that poster I showed you, so it's depending what impresses or excites you. Some people get very excited looking at this. Look at the full sky composite image, which includes both the limbs of CMB anisotropies and the galactic signal, pretty heavily dominated here by very high frequencies. So the galaxy is fortunately not that dramatic at the frequencies where we're looking for CMB anisotropies, but this just tries to show everything. And if you're an astronomer, but not really of the type to spend all his life looking at the sky, you do get excited. I mean, for example, the first time in your life you discover looking at it, not like that this is an Andromeda galaxy, the Andromeda galaxy, okay? It's really big. This is M33, the little blob. If you look at it at great zoom on the map, you'll actually see little spiral arms of it, even on Planck maps. So, Large Magellanic Cloud and Small Magellanic Cloud. Here is a Crab Nebula, famous object and important for polarization measurement. Orion Nebula, the brightest nebula in the sky, visible by naked eye and optical, and so forth and so on. Ophiuchus cloud, which will be an actor in a couple of transparencies later on. So what are we releasing today? The early release compact source catalog and a bunch of papers. The papers are now visible at the website of ESA that I'll show in a minute, and they will come up later on today on AstroPH. The first suite of 7 papers design the mission progress, thermal performance of Planck, all this beautiful cooling system that I was briefly referring to. 2 papers per instrument describing performance and data processing effort, and the paper describing the build-up of the early release compact source catalog. So these are the technical papers, followed by further 18 papers devoted to science, various sorts of astrophysics, and there is a bunch on Sunyaev-Zeldovich clusters, extragalactic radio sources, cosmic infrared background, a lot of stuff on dust in the galaxy, both diffuse and compact objects, and a couple of papers on cold cores or clumps, the star producing regions in our local solar neighborhood. All papers start with the preamble Planck early results in the title, and we author all the papers, and that's how it's going to stay throughout the collaborations operation, Planck collaboration, followed by names in alphabetic listing order. Typically, they will order 200 people per paper. The catalog itself is already visible at the website of ESA, at Science Operations, there, and also at IPAC, at Infrared Science Archive in Pasadena. Papers presently already visible at this website at ESA as well, and like I say later today, will pop up on AstroPH. The session is ongoing at Seattle. Maybe you won't have time to go to that booth. And too bad for posters as well. Simultaneously, there is an international conference running this week in Paris, where highlights of astrophysics of these results are discussed. And there will be a press event, I think there is a press event right now in Seattle, and there will be one in Paris tomorrow. There must have been something by ESA today as well. This is the list of titles of these papers. And from now on, it's pretty hard uphill struggle for this talk, because this is pretty much like trying to go through maybe 30 or 40% of general observing astronomy course in about 40 minutes. Not an easy task, especially if you're not an observing astronomer by nature. So I hope you'll be patient. I didn't sleep much last night. I will probably read quite a bit from the screen, because it's not the stuff I do every day, most of this. We've been through where the data were released, so what's the content? We have sources at 9 frequencies listed, tabulated for temperature only. And we have 2 auxiliary catalogs which specifically list early set of galaxy clusters detected through Sunyaev-Zeldovich effect on the sky, and also an early list of cold cores detected using their spectral signature properties for those star producing regions. So let's go through that. What were the motivations originally for a release compact source catalog? Well, for example, Herschel was launched with Planck together on the same rocket, and like Planck is a cryogenic mission with limited lifetime, valuable lifetime. So the idea, of course, got born that Planck, after its full sky survey, could come up with a list of potential interesting targets for Herschel to immediately be delivered to have success with observations before Herschel runs out of steam. So likewise, feeding other astronomical facilities as soon as possible. The target was to deliver it within 6 months after completion of first sky survey. So for those who don't know what that means, the satellite flies in the solar system, scans the sky, avoids the sun, and a combination of these motions allows it to make an image of the full sky roughly in half a year of observation. So single so-called sky survey in Planck's case is about 6 months' time, a little longer because of idiosyncrasies of scanning strategy. The catalog was actually delivered on the 7th of September to the data processing center. So now I probably shouldn't go into slightly Byzantine nature of all of this. Suffice it to say that Planck is managed through two consortia, both international in nature, one coordinated from France, one from Italy for high and low frequency instruments respectively, and they have their data processing centers serving their instruments, which very jealously guard data and are the only authorities that can release data to anyone. So US activity in that sense is subsidiary, so although all the work on building up the early release compact source catalog was conducted at the IPAC Center in Pasadena, we get data from Europe, we do the work, we deliver it back to Europe, they rerun it on their computers, validate it, release the catalog today. So after, on the 7th of September, the products were delivered from US to Europe 6 days early. Some 3 or so months later in validation, we come today to the great release date. So the characteristics of the catalog, well, of course, the full frequency span of Planck, almost a factor of 30, very wide, all sky by nature. It's the first ever all sky survey that operates between 100 and 1000 gigahertz that is sensitive enough to detect individual objects. It gets particularly impressive expressing it with respect to FIRAS, which is slightly unfair because, of course, it was an old instrument with a huge beam of 7 degrees looking at the sky. So the combination of the very small arc-minute beams of Planck with that 7-degree beam plus detector sensitivity results in 10,000 times gain in sensitivity compared to FIRAS. So FIRAS didn't see any single compact source on the sky. Well, Planck sees quite a few. For the first time ever in astronomy, radio through sub-millimeter all-sky surveys have been conducted simultaneously due to this wide frequency span and 2 instruments on board. In the work producing the catalog, we had to face the difficulty of simultaneously handling very different regimes in source extraction. Somewhere there CMB dominates, somewhere there noise-limited situation occurs on the sky, and then there are dense regions in the galaxy, mostly where confusion with its set in, so you have to concur with that. Again, galactic backgrounds change dramatically over the sky, as the poster indicated. The catalog had to be a little bit early, had a defined reliability that allowed to set up the time sequence for work at the 90% level, whatever. That means this is a table of generic properties of the catalog and, well, instrument combined with the catalog. So, well, nearly full sky coverage, resolution between roughly half a degree and 4 minutes on the sky. Here is an interesting entry, of course, the number of sources being released from a few hundred per band at low frequency, growing through 1,000 to 9,000 at high frequency at 857, and flux limits that were reached in work. The early Sunyaev-Zeldovich catalog contains 189 clusters. I'll show where they are, what they look like. Early cold cores have 915 cold cores. The catalog has 950 cold cores, and we'll talk about that a little later as well. Now methodology, maybe it's not necessary to really delve in that, but there was a bunch of source finding algorithms designed to try to compare all of these regime changes in behavior on the sky maps and checked and compared for efficiency and so forth and so on. In validation, more importantly, the strategy adopted at IPAC was to conduct so-called Monte Carlo quality assessment procedure, which consisted of working with the maps and injecting artificial sources into them and knowing where they are, running detection algorithms and finding out what fraction of them were positively detected and defining based on that statistically what reliability figures are for the whole catalog. Two different algorithms ended up being chosen for delivery work depending on frequency. Foul snakes, the Bayesian algorithm developed originally by Grasa-Rocha, Piotr Kolvaria, and Hobson in Cambridge, and then the older code adapted to CMP developed originally by Emmanuel Bertin in Paris for galactic survey work called source extractor for high frequency maps. A little of a joint bracket on methodology for these two early catalogs of Sunia-Zeldovich and cold core clusters, although they're very different objects. The joining thing is that spectral characteristics are known, and that helps tremendously in detecting or doing some science with the sky maps even without detection. So Sunia-Zeldovich, it's a little tedious here to go through this. Basically you run a bunch of relatively sophisticated filters on the maps which are designed based on models of what cluster's spatial structure is, combined with angular resolution of the instrument and spectral characteristics of the Sunia-Zeldovich effect itself that results in enhanced capability to detect the clusters. Not unsimilar approach to detecting cold cores. In fact, this is more of the classic astronomy kitchen, if you care to go through this. So, selecting on the sky, finding these cold cores is quite an interesting procedure. You use ancillary data from IRAS to locally correct for galactic emission on the field where you're looking for the source. Then you find sources separately at 3 upper frequency bands and only select those which show up in all 3 of them. Select them on signal to noise, assign that universally to the band merge data. Then you perform aperture photometry on 4 bands from 100 to 850, and you make physical fits for temperature, spectral index, and flux at 850 of gray body nature to determine the temperature of these clumps. Then you reject the ones which are less than 15 on signal to noise ratio, and you choose the cold ones. As you will see, these are cold objects in a moment. The whole procedure then results in reducing the number of objects found through these 2 steps to only about 900. That still increases the number of the non-cold cores by at least a factor of 2. The total number that the group working on that detected was almost 11,000. Now it's a quick glimpse of the content of the catalog at each frequency. So we start at low frequency at 30 gigahertz. Color bar indicates the flux density in chance views of the astronomical units. Typical radio sources are between 1 and 100. So you can see a bunch of bright sources, typically in the galactic plane on the far away. Intermediate brightness or faint sources elsewhere. This was the one that had a few hundred, 9 or something. A little fewer at 40 gigahertz, that's the impact of the fact that this is the more noisy channel, okay, than 30 gigahertz. And then slightly larger number again at 70, and then the number starts growing. We hit the higher angular resolution, higher sensitivity operational regime of Planck. So at all these frequencies upward from here, the number of sources grows tremendously, and that's what we see. So this one is, like I showed before, around 9,000 sources in the sky. Well, it's very clear where the galactic plane is. There is a lot of sources which are galactic in nature. There are extragalactic ones as well, as for example these. So this is now the projection of only early Sunia-Zeldovich clusters. This is 186 of them. They are coded in color by signal to noise ratio of significance of determination of the Sunia-Zeldovich signal amplitude in the cluster area in the sky. So you can see that there are whoppers, there are clusters which are hugely significantly detected, almost 30 in that signal to noise, and there is a bunch of fainter ones.
Do you know the redshifts of the clusters?
I'll show you in a minute. So, I'll come back to that. The early compact core catalog has this distribution of objects on the sky. If we plot it, this is, believe it or not, 900 objects actually on this plot. If we did a plot of all 11,000 they detected, they would more clearly indicate that these objects are seen pretty much everywhere in the sky with strong concentration to the galactic plane. In the 900 it's more clearly centered on the galactic plane, and in fact very remarkably follows the known maps of the distribution on the sky of carbon monoxide, tracing molecular gas, cold gas in the galaxy. Some points about the properties of the catalog. There is no claim whatsoever on its completeness. It's not a classic catalog in a sense of any flux density limit or completeness of the sample. It was not designed for that, and in fact it should not be used formally and blindly for any sort of source counting exercises and stuff like that. It's based on 1.6 sky coverages, so that has implications. 40% of the sky was observed once, 60% of the sky was observed twice, and averages were made where appropriate. That has impact, of course. There is variability in sources. This is being followed up to understand what's the impact of that. Of course, there is impact on determining flux, for example, if 2 observations are averaged. There is an issue with the width of the bands on HFI detectors. 100 and 270 gigahertz bands are broad enough to encompass the molecular CO lines, and you have to be very careful separating that. Quite a bit of work went into containing this problem. Significant fraction of sources in the high-frequency HFI bands can be associated simply with interstellar features, Cirrus features in our galaxy that we knew very well about from IRIS. Now back to clusters. So that's just a couple of lines on the classics of Sunia-Zlodowicz effect. So in 72, Sunia-Zlodowicz made the observation that if CMB comes from redshift 1,000 photons coming to us, they hit a cluster on the way. If the cluster is massive, if it contains the gas heated to over 10,000 Kelvin, so it's ionized, the photons going through it will get scattered or hot electrons and shifted in their spectrum, and even though the fraction of photons who actually undergo scattering going through clusters, there is a photon-preserving energy shift for the aggregate of photons coming through the cluster, which results in a slight distortion of the spectrum, which would be black body at average temperature of CMB otherwise. So for a very long time, when CMB were concentrated mostly in the radiometric regime, this resulted in actual depression of temperature. So the expectation was that you look at the cluster and you're going to see it slightly colder than the environment in the CMB photons coming through, because they were shifted to higher energies. Now Planck goes so high in frequency that of course it goes to the other side, and in fact it was designed to address this issue by spread of detectors such that one of them sits at 217 gigahertz where the 0 point for this spectral shift occurs, and some of them operate below to see the decrement, and some operate above to see the increase in temperature of photons coming to the cluster. An example on the particular cluster is shown here. So clearly at 100 and 143 gigahertz, that has a cold spot detection matched by hot spot detection on the high frequency side with nothing in between. It's the first all-sky survey of clusters since the German X-ray Rosat satellite in '92. It finds massive clusters. It's good for cosmology. It's easy to follow up because when we find them, we know where they are. We know where to look. So far, only 889 were found. There are various issues with this. I mean, a long story of this. I mean, when Planck was proposed originally, 15 years ago, cosmology was at the stage where people expected something like 20,000 clusters to be discovered by Planck. All of that is a very strong function of what we know about the structure of the universe and parameters like sigma 8, for example. So since the knowledge of those has changed, well, unfortunately for cluster finders, we went from the regime of many thousands to perhaps hundreds of order thousand in the end when we have the full sensitivity and all sky surveys aggregated. Out of 189, 169 were previously known. So presumably all of them had known redshifts. So then the remaining 20 were being followed. 11 have been already observed by XM and Newton, European X-ray satellite in snapshot mode, and one of the posters, I won't show it, but you'll see it on the web in the papers, shows beautiful X-ray maps of these clusters. So that there are clusters there. These are typically fairly low signal to noise for that scale that I show for Planck clusters, and there is already morphological assessment that from high resolution X-ray data analysis, it's clear these clusters have fairly tortured morphology to show systems which are not relaxed in the process of some action going on. One extra, this confirmed by another instrument, and 8 are still in the process of having follow-up observations. This is the distribution of these clusters in the sky. The blue ones were known, green ones got confirmed, red ones are waiting for confirmation. It's a matter of staring at this. I did before I came up on stage. If you knew how in this galactic reference frame Planck scanning strategy works, integrating most often close to ecliptic poles in these locations, and least often crossing very rapidly and sparsely the ecliptic plane, perhaps you start seeing that, for obvious reasons, data is more noisy here than there. There seems to be a little bit of preponderance of clusters in those quadrants as opposed to these ones. That's probably driven by that. Some statistical snapshots of how this cluster sample, the early years of rubbish sample from Planck, compares to other work, and not very high quality plots. Sorry about that, they were just cut out, not in original form, just from the PDF, so the resolution is pretty crummy. It's the same plot on the left and right, just to confuse things with different color coding, but it's the mass in the units of 10 to 14 solar masses on the horizontal axis linear, and the redshift is linear here or logarithmic there. And it simply shows Planck clusters with those triangles, with the whopper that was described, the very massive one that was described in the press release in July, I think. Compared to Rosat clusters, serendipitous clusters, the South Pole telescope clusters, the qualitative differences are very clear. The South Pole goes deep in redshift, but typically observes rather lower mass clusters, until of course a few days ago where they found one that sits here, that's very massive and a very high redshift. So, well, the game's on. It'll be interesting to have combined cosmological implications of that. If you look at the plot of redshift versus X-ray luminosity, you see that these Planck clusters sit typically on the high edge of luminosity for redshift range they are in, compared to, say, Rosat clusters or the others. This is a composite of a little review of some of the detected clusters coming from very famous well-known ones like Planck here in the second panel. These, I don't know if it's visible, is labeled with the signal-to-noise ratio qualification of detection, so this goes almost to 30 in this case, drops down to around 7 in this case. Well, we can see the gradual morphology shift from very big, massive, fairly relaxed clusters to stuff that starts showing fragmentation even in this kind of very heavily smooth plot. Then, other than just categorization of the compilation of the catalog and its statistical properties, there is a few papers that go to a slightly different type of work on clusters, trying to link what Planck sees with other existing astronomical knowledge. So there is a MAX DCG catalog of optically selected clusters derived from SLUM data. It contains a huge number, almost 14,000 clusters, defined as agglomerations of clusters detected around red galaxies detected around bright central galaxies. Typically, bright central galaxies have known redshifts and serve to validate the general methodology of getting distance information from photometric redshifts for the other galaxies. It covers 7,500 square degrees in the northern sky. It's described, that's an attribute of the catalog, by the richness measure. In the interest of time, I will not even attempt to explain this. It's just counting galaxies in some region of the sky, determining where the clusters were. And then it comes associated with the follow-up work from, in particular, a paper by Rosa in 2009, where that richness category for the cluster is linked to determination of its mass through some considerations of statistical nature. And then we have Planck data, which we use in the following way. We take the positions of these almost 14,000 clusters, we look at these positions on Planck sky maps, and we apply the filters to detect multi-frequency-wise the Sunyaev-Zeldovich signal. And typically, of course, as I told you, we have determined there are 169 clusters that we discovered, so of course we're not going to see 14,000. That data gets binned and results in relations of this nature that I will describe now with some pain. So Martin was nicely sarcastic enough about astronomers labeling things, calling them, and so forth. I mean, I'm not even going to encourage you to try to understand what these things are. It's just a measure of X-ray luminosity on horizontal axis versus the measure of Sunyaev-Zeldovich signal strength of a vertical axis. Derived in a certain way. If you're an aficionado of that, read it in the paper. It's painful. X-ray catalog and optical catalog are projected here. So I mentioned on the previous slide Max VCG, which was optical. There is a meta-catalog of X-ray selected clusters, which is an agglomeration of various resources built on Rossat and other observations using X-ray machines to build a catalog of about 1,800 clusters which are X-ray detected and have Sunyaev-Zeldovich signal. So let's actually start with those. So these are in red. The number of clusters which went into a bin plotted is indicated here. So if you add those red numbers, that should be about 1,800, I hope it is. Okay? And these are X-ray clusters, they have luminosity determined, so you just plot one versus the other, this is your data. So this comes from Planck side, integrating Sunyaev-Zeldovich signal on Planck maps at the position of X-ray clusters for which we know luminosity. Nice relation. Let's extend that work, go back now to optical catalog, do the same, obtain the measures in bins, vertically speaking, of Sunyaev-Zeldovich signal, but translate now the richness of the catalog to luminosity through modeling step, which is based on what people in X-ray do, based on our new models, supposing clusters have certain radial profiles of pressure, density, temperature, and all of that. So this is translation of optical data into an X-ray category that's plotted, categorization that's plotted on the horizontal axis. The whole point of this plot is that in a classic astronomically painful way, you determine phenomenologically from the data, plus some model support, empirical relations that are useful for guiding further work. This is a pretty impressive stretch in luminosity, and it basically tells us if we look at the cluster new one that's statistically consistent with the catalogs we're dealing with here, and it's got some luminosity, we predict that it's going to have the Sunyaev-Zeldovich signal in this vicinity. That's what people do, it's important. But there are caveats, and one of the papers reveals a caveat in some element of this thinking that is not yet very well settled, which is repeating the same sort of procedure that I just described, expressing directly in optical case as a function of richness of the cluster, the Sunyaev-Zeldovich predicted signal. So that's a repeat of the previous plot with a different axis here of the native quantity to the optical data that are plotted in red, the relationship that we determined from Planck. So again, optical catalog, almost 14,000 clusters, richness given by that optical catalog, Sunyaev-Zeldovich integrated at the positions of those clusters, bin, plotted, empirical relation. Modeling step now. From richness, we can go to mass through this Rosa relation built for this catalog, linking it to weak lensing work on determining mass of clusters. And then from mass, we can go to Y through our new models of X-ray and Sunyaev-Zeldovich connections. When you nest these two, model prediction comes off quite significantly by a factor of a good few. And this has given a pause to people who wrote it. The paper is out. We don't understand why it's like that. it has to be juxtaposed with the previous plot. I was amazed myself. I mean, here optical and X-ray looks good. Here it doesn't. Well, it doesn't because horizontal axis is different. So you can look at it different ways. You take optical data, say richness to Sunyaev-Zeldovich relation comes low for Planck measurements, given what people routinely model for Sunyaev-Zeldovich field. And what does that mean? One wink on this is that work was redundant, selecting out of this Max BCG catalog only those which have X-ray counterparts, which reduces it to only a few hundred. And when that's redone, the whole procedure on smaller number of clusters, theoretical and empirical optical combined X-ray relationships agree. So there is a speculation, maybe there is a detection of a new subpopulation of clusters amongst optical clusters, or just some new empirical relation dug out. We don't know, follow-up work will show. This is what Planck says. This is just a quick snapshot of validation of this work by running the same procedure on Planck sky maps to assess the Sunyaev-Zeldovich signal and cluster, but randomizing positions, not looking at positions of the Max BCG cluster objects. The signal goes to zero, compellingly. So on statistical level, there's no issue. There is something we're looking at, and we need to understand it. Follow-up work will be committed. Okay, extragalactic radio sources. I will be brief on that. The extraordinarily large frequency range from radio astronomy point of view, almost never were there surveys going as high as frequency to study radio sources as Planck provides. So a sample was chosen to be cooked at 30 gigahertz, various conditions of rejection of possible galactic contamination, Magellanic cloud and everything applied, reducing the sample to 533 extragalactic sources, which show completeness above 1 Jansky flux, and studied for confrontation with theoretical models. So there are people like Gianfranco Bezzotti and others who build models of counts of radio sources. This is 6 plots of differential counts of radio sources, a function of flux from 30 to 217 gigahertz. And just very quickly what they show is, first of all, this is the cutoff on 1 Jansky that I mentioned before, above where we have completeness. The counts up to 100 gigahertz from Planck data lie very nicely on theoretical predictions of Bezzotti and others. At higher frequencies, Planck begins to see deviation, and sure enough, radio astronomers will have to come up with explanation of that. These are just snapshots of a bunch of sources that have not been found to have counterparts. So this catalog of 500 something, like you mentioned, that was mostly known sources consistent with WMAP and other radio astronomical observations. What comes out in the search on the sky for sources returns things like that. So these are 3 frequencies at low end from low frequency instruments. Sometimes we indeed see it as a source at the center, even though it's faint. Sometimes we see diffuse structures which probably won't render real sources at the end. It will have to be studied in the follow-up. For radio astronomers, what's interesting, most of them have relatively flat spectra. Some of them are blazars, which show peaked spectra. They seem to be synchrotron dominated even at high frequencies. Very few dusty, if any, galaxies found amongst them. No compelling evidence for a new population of previously unknown radio sources. Another type of study of radio sources is shown here. In the northern sky, a big campaign has been commanded to push resources of quite a few existing radio telescopes and then optical and X-rays to do simultaneous observations with Planck during Planck's scanning of the sky. So compilation of all of this aggregate resource resulted with 104 sources used for studies of spectral energy distribution in radio sources, and a few examples of it. So we have tremendous spectral coverage. Now Planck is hidden here, and in the zoom of Planck frequency, you see 3 frequencies from LFI and 6 from HFI, which just simply sits so somewhere here, so it goes all the way to optical X-ray. Archival data are shown in gray. Simultaneous observation with Planck are shown in color. Fits are done with polynomial low-order fits for synchrotron and reverse quantum spectral bumps. And so they study them and discover that there are spectral grades and things of this sort of nature which Planck is fortuitously placed frequency-wise to help constrain. A lot of follow-up work to do. Now we'll move from outside of the galaxy to inside the galaxy. Most of what I'm talking about is on sources. I didn't really talk about the diffuse component very much. This is a little bit about going diffuse, but very specifically targeting the subject of so-called anomalous microwave emission, or what often is called spinning dust emission, based on one of the models that was devised to help understand what may be happening. So we look at a very specific cloud, this row of Fucus molecular cloud just above the galactic center that I showed you on the map in the beginning. You see 6 frequency snapshot pieces of map for Planck, 5 by 5 degree on the side, so that's pretty big. These are very well resolved objects on the sky, and 2 auxiliary data fields in H alpha and at low frequency to hook up the free emission models on the field. Morphologically, you see that from 857 to 70, you see the similar looking cloud, and then something flares up at low frequency. So that's precisely the manifestation of what some people think is spinning dust contribution in a particular object. And spectral image of this looks like this. So frequency, again, Planck from 30 gigahertz to all the way here. This particular object, where the electromagnetic spectrum is fitted on the small field that we looked at, shows the Planck data measuring very tightly the dominant cold dust emission in the region. This is CMB, which is outshined by cold dust, and the little hump that has been traced by WMAP data, and now Planck provides some more. So the overall spectral fits after this dust contribution, very well nailed by Planck, is removed, and CMB is removed, leave these 2 components, which is, in the case of this particular source, provide a relatively compelling fit for combination of 2 gas components of high-density molecular gas and low-density atomic gas present in the cloud. Interestingly, on those CO lines that I mentioned, I'm not sure how the fit was made. In the process of fitting the theory, these 2 points were discarded because on this particular field, this shows you at 100 and 270 gigahertz how the molecular CO line is contributing to the flux and completely takes it away. So eventually it will be modeled, I'm sure. But right now that's what it looks like, as a direct manifestation of how carefully you have to be doing this sort of thing. The paper that addresses this issue, this is the Ophiuchus cloud again, describes 4 regions in various places around the galaxy. Maybe somewhat excessively describes it, it's everywhere, but they got excited. Now, infrared background. This is radiation coming to us in aggregate, pretty much vacuum clean from all the galaxies that we're looking at, to high redshift, dusty, star forming, anything in the infrared. Important probe of what's going on with star formation in the universe at redshift up to where stars are formed. We will show on the next transparency that maps are highly correlated at high frequencies, decorrelated at low frequencies, as expected for this sort of effect, since different layers of Z contribute to different frequency images of the situation, and significant detection of CIB anisotropy has been made with Planck data. It's compelling because, considering that we assume that this is all just emitted by these galaxies, and there's so many of them far away that we don't resolve them, so it's an unresolved, continuous-looking signal composed of grainy galactic contributions, and that's all that comprises it, then spectral signature of this anisotropy of that signal should be consistent with the average determined before from older data, and I'll show you that it is. And it compares compellingly well with prior determinations of this. Here is a snapshot of one of the fields. The paper addresses analysis and modeling in 6 fields on the sky. This is one of them, and shows 4 frequency bands from HFI in raw data. So here you see everything. Still CND anisotropies and sources, progressively going into some other stuff. There is a fairly painful procedure of cleaning it and producing the residual maps, which are supposed to be free from CND source contamination and galactic cirrus. And this is what it looks like after all the processing. Well, it's fairly compelling visually that the high frequency down to this one, you visually can assess correlations which then disappear at very low frequency, which I just mentioned. And the power spectrum analysis is run on this signal as anisotropy of the sky to quantify it. First of all, it's plotted here as a function of electromagnetic frequency. So this is just integrated power at those 4 bands between multiples of about 200 and 2000, where the spectrum was estimated, angular spectrum in the sky, in comparison to older measurements of CIB from older instruments for the average effect. Okay, so that's a pretty nice demonstration that anisotropy detected now is consistent with average known before spectrally. And then the spatial image of this is, of course, as I said, the L-indexed angular spectrum from L equal to 200, so roughly, about a couple of degrees on the sky. The deep fields I showed incidentally were about 5 by 5 degrees on the sky. Right? So this is corresponding to angular scale less than half of the size of the box we looked at, all the way to 2000 arc-minute regime. For aficionados, there is a lengthy description of modeling work that went into understanding the measurement points. What's important on a crude level for right now is that clearly there is signal. If you throw at it simplified modeling that includes contributions from just linearly modeled distribution of galaxies in space according to linear theory and correlation function derived from that with a constant offset and shot noise contribution on such measurements, then, well, maybe I said it wrong, it's probably what you think. I want to confuse myself, but anyway. The whole point is that linear theory comes down at low L's and meets what observations tell us, and then observations take off where expected is the nonlinear behavior in the distribution of spatial structure as imaged in the CIB anisotropies. So, a matter of some debate internally. If you speak to Martin Weidel, who's here or not, he will tell you that it's enough to shoot straight lines here corresponding to just power law fits for correlation functions. We know that they are power laws, and at 5 megaparsec separation, which we're reaching here, correlation functions obviously are not linear, they're non-linear, and the data conforms to that. So that holds up the whole picture together. Now, how deep can you go on very detailed modeling of how you would vary underlying theoretical explanation for this is a matter of opinion, and it will be an ongoing discussion, but clearly the paper brings about wide frequency based, very strong detection of the signal on those 6 fields. So we've gone through clusters, we've gone through radio sources, we've gone through some stuff in the galaxy. Now we're going back home to Puerto Vallarta, so cold cores, the nearest neighborhood, as you will see momentarily. So I think we said that maybe before, 100 micron data used to clean the fields, find those almost 11,000 objects, which through ruthless selection gets reduced to 900 for release today. Small subgroup of 10 maybe were already observed with Herschel in a key project with much higher resolution to study further what's going on in these objects. There is semantic evolution of what we're looking at. We're still using the name called core. People argue they should be called something else because they're kind of intermediate in a sense physically between true cold cores making stars and molecular clouds. If that excites you, be my guest. Cold core population characteristics, the temperature found, these are very cold objects. So the coldest found, 7 Kelvin temperature determined, and that's the coldest cold core ever found, okay? Average 13, the warmest is 17 Kelvin. So as one of the press release one-liners said, the coldest object in the solar system, namely Planck detectors, are detecting the coldest astronomical objects in the solar system. Something like that. This is where they are. On a sample of 2,600, distances were determined in various ways, and they turned out to be mostly within 2 kiloparsecs away from us. As I showed before, full sky, but centralized on the galactic plane, compacted right on the galactic plane. There's a short table of their properties. So these are what? Fraction of the solar mass to some thousands of solar mass objects with very cold temperatures. And there are a series of stars. So that's how far Planck takes us from star formation to clusters of galaxies and CIB in a single shot of release of only 10 months of observations. Summary. Since August 13, we launched in May. August 13, it started observing the sky. 3 months it took to get to L2 point, cool down, and be ready. 13 we started observing. 10 months later, data went packaged for every release contact source catalog work. Of course, our principal target is cosmology. For that, you will have to wait 2 more years. It's still preliminary. Data is sweet. This is a 3rd generation instrument. I wish I could show you what we see already, but I can't. So be patient. But I think that the menu of stuff that can feed other types of astronomy and astrophysics to the results released today is truly tremendous. And it's a great moment to put a dot in there. And the final one before the final picture is most of the work conducted to derive the science, some of which I was immediately showing you, was conducted on maps like this. So internally, we produced maps where, as good as we could, for the present state of the mission, we removed the CMD, so that's why I can show you that. This is everything that we don't like in the sky, if we want to do cosmology. Incidentally, just final thoughts. 70 gigahertz, I told you, was a sweet spot for galactic emission. You can clearly see that the extent of the galactic plane vertically is the smallest of all frequencies. These are the least foreground infested channels, so you see most clearly the actual imprints of the noise. So these wedges here is precisely what I was telling you, 10 months of observations, that the particular way of Planck scanning the sky makes this region observed twice and this once. That's why these wedges are visible there, and elsewhere not so well because foregrounds actually start dominating and get more significant in amplitude and noise on the maps. We have to beat the noise, we have to beat the foregrounds. We're ready. There is quite a few of us. The final slide is a collection of logos, not all of them, quite a few people send them. There's a sampling of institutions from which people come to work on Planck. Like I said, an average paper in the suite you're going to see today carries over 200 authors, and I guess that's how it's going to stay. So next time, 2 years' time. Thank you.
Any question?
Two quick questions. One, when should we expect a release of the polarization properties of the foregrounds? And also, is there a released map of CO emission based on the 100 gigahertz band?
Not today, I don't think. The answer to the second question. I don't think there is a set date for polarization foreground release, if you will. So right now we're working under the assumption that in 2 years' time everything will come in aggregate. We'll see how it goes. Polarization is a very tortuous subject.
Any other?
So you showed some correlations of the SC signal with optically detected clusters as well as X-ray. Have there been other correlations studied, say with frequency?
I don't think so. Just in that area, actually. So it's weaved into the fabric of it, but I don't think there was a dedicated effort otherwise. Yet, anyway.
One last question? If not, we thank our speaker again.